Yeah, so I'm collecting homework up here at the front. Yeah. Yeah. This is looking in, yeah.
Yeah, I just forgot my watch in my room.
Yeah, don't worry about it.
Can I do anything now?
Later or something, yeah. But anyway, it's not too critical at this point, so don't worry about it. But I think it's impressive. All you have to do is say that you don't have to do the homework, and homework submissions are even more than ever. So if you don't worry about it, if you want to make sure you should be doing your homework. So the right thing, I think you're understanding I'm spending about 50% of my time on this, but my idea is the homework's extremely important, and you should do it, but it's sort of like, on the most part, not part of the grading. So you should be doing it. So the things that should happen, you should be doing it on time. You should come to the recitations unless you're really solid. And yeah, there's homework goes in there. And up until the first midterm for everybody, it won't count. And things are going to be only monitored carefully if it's sort of strong signs that you're not working. But I mean, I got good feedback that a lot of you came to the recitation. That's good. So that's a good yeah, everything. I mean, I'm not surprised. I'm not wanting you. I'm pleased to see you turn it in. But I just have this policy. There's no incentive for you to really copy the homework and turn it in. Okay? Because it's important to do it. And if you do it, it's good. If you're not sure that you're going to do well, it's good to anticipate that and turn it in so you have a record of turning it in. But if you do it late, that's okay too. You can turn it in and it'll be indicated. Then, assuming you're doing fine when we come to the midterm, this all will continue. And if you're not doing fine, it's going to be unpleasant. I mean, so I think of it as a very strong encouragement not to slack off and to work hard at the beginning. And if you do that, everything will be okay. If you don't do that, you'll regret it. And that could, in some cases, so in one reaction to where we are now, you're starting the second homework. This is all review. It's review of probability. If the first two homeworks on review are in fact very difficult, and it's not ever surprising that the problems would be hard and you'd need to look at the answers. But if you look at the answers and you really don't understand it, I mean, that's probably goes with that you didn't get a good grade in the probability, or you somehow never took it at all, which would be you're in the wrong place. So if you should yourself use this as a diagnostic, there's like the previous course is 4150 or 30. There's a previous probability course. If you're not solid in that, you really shouldn't be here. You should be doing that instead. And you should recognize that now's the time to sort of see for yourself. You're doing a couple of homeworks. Convince yourself that you belong here. If you're struggling now, take the other course. If you need to do probability, do the other course. Okay? Try to figure that out for yourself now. Okay. That's so we're collecting the homework. That also looks impressive. That's a pretty big package of homework. There it is. Turn that in at the front. But all that's going to happen at this point is it's just going to be checked. We're going to see that you did it. Maybe we'll weigh it to see that there's enough pages that it looks like you did it all. So you may get something back that says 1 or half. You might get something about half of it. It's obvious you didn't do much of it. But okay, but we'll just keep roughly monitoring what you're doing. Okay, now that seems like all I'm emphasizing is how I'm checking up on you or I'm not checking up on you. I want to also, in this point two of feedback, is rather than just wait till the end of the term where you get a chance to have revenge and review us, I encourage you to do something like that early. So in particular, one place where I'm not going to go to the recitation and monitor the TA. I mean, the TA is responsible. I'm confident he's going to do a good job. But if you have feedback like, whatever, there's no language issue, but it could have, in this case, there's no language issue. It could be an issue like, I can't understand what he's saying, or he speaks too fast, or he speaks too slow, or whatever, or whatever your reaction to if you have some constructive criticism for the TA, make it now, and make it through me, and I'll filter it and pass it on so we can adjust and move in the right direction. And similarly, you can make constructive criticism or whatever to me, and you may influence what happens going forward. So there's still 90% of the course to go. So if you have some reactions, you can do that. Okay? I may not pay any attention, but anyway, that's welcome. It's welcome. Okay, then, as I'm going to start developing today, I'm going to, part of this is designed to make the course work for people with different backgrounds. So at one level, I'm trying to make it so that the exams are not too hard, the homework's not too hard, and it's going along doing basic stochastic processes like Ross's book. And that's fine, and that's a reasonable goal. Some of you are well prepared to do a lot more, and I want to offer you opportunities to do interesting things as extra credit stuff. And the people, I'm expecting that in these extra credit projects, 2 or 3 people might do any one of these. That's what was my experience last year. So, and the general idea is, in my mind, that these will not penalize anybody else. So I'm going to grade the exams, and then if people do, there's going to be some sort of grading based on the exams. And if people do extra credit, that's just extra. It's not going to affect, their grade might go up, but it's not going to be part of a curve. I'm not going to sit there. So you're not obligated. The idea is you're not obligated to do these extra credit projects, but if you want to do them, they're things to do. So then I'm going to introduce a couple of those today. Okay. So the idea is it's indeed extra, optional, and the idea is there are things that would be interesting to do, and it's a question of whether you have time to do it and so forth. So you probably shouldn't do these things. Well, if you're struggling, you should put your effort on doing the mainstream of the course. But if the course is going along easy and you have some slack, if you're taking 21 credits, you probably shouldn't do this either. But if you have some slack and you're interested, these things will be designed to be something that would be interesting to do, and which would be interesting to me too. So okay, so this general theme of where we're going. Now where were we before? Okay. Well, before we had this. Okay, so now we're back on track. I don't know. I'm not putting the same numbers here, I guess. This is something like what we had. I guess there was 2 versions of this, whether I tossed the coin 1,000,000 times or whether you did. And I guess I left it with the example is that I did this. I claim to do this because I was not assuming that you would be crazy enough to do this. But let's say I tossed, or I told you that I tossed a coin 1,000,000 times. And then these are my numbers of heads, and I count the number of heads. And these are possible numbers that I could tell you. And then the question is, what do you think of that? And this was where these are sort of the numbers. And one thing you're seeing is, if you thought of, one perspective of this is, if this were a totally accurate experiment in the sense that there was no randomness, we would deduce the probability of heads as being this number divided by 10 to the 6, right? So down here, it would be 0.598, and here it would be 0.506. And here it would be exactly 0.5, and this would be 0.501. So if this was, if this outcome, we just took the fraction, we would have a direct estimate of the probability of heads being this. But anyway, I guess, so what do you think of these things? We quickly got to the right key points. The first level answer was this sort of 60% heads just isn't believable. It should be close to 1/2. So this last one is not believable just right away. And then actually this outcome, this is very important, I think, in terms of thinking of modeling. This first outcome is not believable, even though this is the single most likely outcome. It's just too exact, and its individual probability is small. I mean, you can compute it, and it'll be like 1 over 1,000 or 500 or something. So it's very unlikely that you'd get exactly this. So this is not very believable. Then you're thinking about these, and actually there's sort of two issues here. One issue is what you really think the probability of heads is. You know, if you tossed it a billion or a trillion times, what would it, and he did it fairly, what would it come out to be? And maybe it's not, it's believable if you tossed it enough, it's not really 1/2. I mean, it's some physical thing, the coin, and there's the coin. I mean, it's probably, it may be that the coin, you could start to get into all the probability. It's probably true that the successive tosses are not independent quite. Very hard to make them independent. That actually doesn't matter too much. But what will matter is if on any one toss, the probability of heads is not quite 1/2. Maybe it's 0.5001. Eventually, if you toss the coin enough, you'll see that it's not 1/2, if it's not 1/2. By the law of large numbers, after many, many times, it'll be whatever it is. So these answers here are not too crazy because this is off by 1 part in 10,000, right? So even if this is accurate, there's no randomness. If this was after 10 to the 10 things, we might not, is the probability really not quite 1/2 by this much error? So there's an issue about what could the real probability of heads be? How much different from 0.5 would it be? Okay, and that's actually a fair question. And somewhere in here, you may not be sure of this, right? And I'm thinking, my thought is, this is, you have your own, this is just an opinion. My opinion is that these are all too far away from 1/2. It's really pretty close to 1/2, closer than these. That's my thought, okay? But that's an issue. The issue is, what is the real probability of heads? Now, my second part of this is to assume that the real probability of heads is exactly 1/2. Forget the error that it might not be exactly 1/2. Now then, you assume if it's exactly 1/2, how likely are these things? But remember, now I've separated the issue. One issue is what's the true probability of heads, and the other is if it is exactly 1/2, how likely would I see these outcomes? And that's the part we want to be clear about. And yeah, and the point here, well, topic advertised here is central limit theorem. So this is my favorite topic in probability, and it's a big story, but it's part of the story has to do with this. So we already did one of these problems. The exact distribution would be binomial, but the key point is the approximate distribution is normal, and what we care about is how many standard deviations from the mean are what we see. If it was exactly, if the probability, the true probability of any outcome would be binomial, which would be this. This is for any k that we might see. The probability of getting k, then n would be 10 to the 6th, and p would be 1/2. Right? This would be the exact probability. If we made a model that said the coin has exactly probability half coming up heads, and all successive tosses are independent and identically distributed, and we took n tosses, the probability of getting exactly k heads would be this, where p is a half and n is 10 to the 6th. And we'd sum a bunch of these up. Well, so then what about these? Just like this, the probability of any individual outcome is small. So when we think about, are these strange, we're thinking about, well, since we're thinking above 500,000, is something this big? So anything bigger than this, right, we're thinking of, this big or bigger, is that strange? Okay, I'm just orienting it. And actually, the big idea is this exact thing. It's a very big idea, is that you want to go from this exact probability. The model fits great, and this is the exact probability of each outcome. You want to go to the approximation, because the approximation is better than the exact thing. This is a mindset. This is a standard engineering mindset. You don't want to calculate the exact stress on the beam. You want to understand if it's within the right order of magnitude. You know, you're doing civil engineering. Engineering, you want to understand. Approximations are often more important than the exact calculation, typically because the exact calculation is under some assumptions that aren't nearly correct. So you don't care. It isn't really meaningful. But here you want to think about the approximate thing, and the approximate thing is that binomial is approximately normal. And therefore, normal with a certain mean and variance. So what's the mean? The mean in the binomial is NP, and so 10 to the 6 times 1/2 equals 500,000. The variance for a binomial is NP 1 minus P, so that's 250,000. And the standard deviation is the square root of the variance, and that's 500. So this is the thing you would compute instantly. In the 1 minute that we talked about it, or the 3 minutes we talked about it at the end of the last class, you would have done these calculations. Mean is 500,000. That was immediate to you to begin with. You'd calculate the variance and the standard deviation, and you would say the standard deviation is 500. So this is less than 1 standard deviation above the mean. This is more than 2 standard deviations above the mean, but not much. This is 12 standard deviations above the mean. This is 40 standard deviations above the mean. These two are totally crazy given the model. Just almost as bad as this one. Because the normal distribution, you don't see things that are 5, 6, 7 standard deviations above the mean. So these things, even this one, which doesn't look too bad, just 6,000, you know, the probability is only like less than 1% big, right? The 6 out here out of, I guess it's about, out of 500, it's 1% large, but it's way off in terms of standard deviations. This is very likely. This is kind of like if you saw this, you'd have no complaint. Around 1 standard deviation high, this would be kind of typical outcome, much better than this, much more believable than this. This is getting a little bit large, but okay. This is in the range where something this big would be like 2% of the time, but maybe. This is totally believable, and then this one is much more believable than this one, right? This is kind of a standard thing, but this is getting a little extreme in these two. But the point is, the point that you should be making, and you actually have to sort of do the calculation, is to see that these two are not reasonable. This is obvious, just bam. You don't calculate the standard deviation at all. It's just totally clear, as you said before. Okay, now, now we come to elaborating on this, because many of you will know this fact and not know the more general fact, which is really important. In other words, usually, almost always in the elementary probability course, you talk about the binomial distribution, Poisson, normal, and you're told about how the normal is approximation for the binomial and the Poisson. So this is all sort of standard, that when you have a binomial, you could replace it with a normal. That's kind of familiar. If that was all it was, this wouldn't be so important. Yeah?
So I understand that, well, what I'm confused by is 5,312 the exact probability of getting 5,000.
Yes.
Exactly. So then why is that more believable? I understand it's with one
Okay.
patient.
So one aspect of this is the statistics. In this example is the fundamental idea of statistics is buried in here because we've got data. Well, statistics today is computing a lot, because statistics today means you just have you're with a fire hose, data is shot at you, and you have to learn to manage just humongous tons of data, and you've got to be good at computing to handle all this data. So instead of as time is advancing, the data that we have to work with grows exponentially. Here, we're this is sort of, the engineering view is not to be buried by the data. We're just given the results. And in fact, we're giving possible single result that I did this experiment, which probably took me a long time, and I'm telling you one of these results, and you're thinking, what do you think of it? So actually, the data that you're given is one piece of, datum, right? One datum. And now, but the point is, even though there's one datum, it's deliberately, I've made it simple. I'm not giving you the tons of data. I'm giving you just one. So the issue is, how do you think of it? Now, in the real world, you got a lot of data. You actually got to collapse it and think, how do I look at it to produce single things to think about? So here, when I'm actually seeing this, say, and I'm thinking about it. So let me emphasize that when I want to say, are these numbers somehow believable, it's very important that I have to couch the question correctly, or at least when I think is reasonably. So part of the point is any one value is not likely. So when I'm thinking, is this unlikely, let's say, I'm saying this is unlikely, I don't mean the individual value. In order to pose the question well, the statistics well, I'm thinking, is a value like this or larger? Because I'm thinking of this as a possible realization somewhere, and I could have seen anything like this or this big. So I've extended the question not to the one value, but to anything bigger, right? That step is very important. You think any one value is unlikely, and I'm thinking, well, is something this big, anything this big, how likely would it be I get this and something bigger? Now in the model, that's, in the picture of the distribution, which is sort of normal, I'm actually, in this normal, it's binomial, but it looks a lot like this. Well, in that case, I'm over here, right? In this case here. And in this case, I'm sort of here, where there's some curve here. In the other case, I'm somewhere here. So this one's here. Well, the other one's right here. So the only thing wrong with this is it's particular. The thing that's wrong with it is a whole other way of thinking, right? The way of thinking is, this is too good. Now you're actually reasoning differently, right? So you actually introduce the reasoning that seems appropriate. It's not like you're a robot, right? Most of the time you're thinking, are these values or anything larger possible? So something this big possible. Here I actually changed the reasoning, right? I mean, it's not different reasoning. It's just too exact. I'm trying in some of these examples to avoid just being like a robot that you crank through the thing. You should think, it should make sense to you that you'd do that. It would feel to you that if I told you this was, you wouldn't want to hear me tell you this is the best one, because you wouldn't believe it. At least 90% of you would not really believe this answer was the most credible one, I think, right? I mean, it makes sense. And that's all I'm saying is that in many of these problems, it's like the game show problem. I'm thinking your reaction to the game show problem is you would be uncomfortable. And you would realize, after we discussed it, I think that has something to do with why you're uncomfortable. Okay.
Could be that the probability of any number happening that you ex ante had in your head, any particular...
Yeah, would be equally. So if you said pick any number that you were thinking of in advance, if it was a discussion, and then if you said that was the exact, then that would have the same character as this as particular, right? If I cared about this somehow, and then this is what you said, if we were talking about it, like beforehand I said, well, I wrote this number here, and then, I wrote this number on the board, and then tomorrow you came in and said you did the experiment and you got exactly this, right? So our attention was focused on this. And this, too, is even less probable. Once our attention is focused on it and you get it, we don't believe it, right?
You can't help but have in your mind.
This. Yeah, that's right. It's psychological. It's the center of the thing, right? It's sort of, our mind is focused on this as the theoretical average, the most likely one. So this is psychologically, it has given a high weight, but yet it's not really much more likely than this. Yeah, well, Michael?
I was just going to say the same thing. The question isn't then what's the most probable answer. The question is what's the most credible answer.
Yes, that's right. Exactly.
And
answer
is certainly 500,000. But what you're really saying is that the second answer is the most probable, because what you're really considering is the set of answers that are within one sentence.
Yeah, exactly. The criteria differ. Yeah. So there's more. Part of this is the business that I'm trying to emphasize is part of this is the mathematical model, the analysis of the model, straightforward, which would tell you this is the most probable and then credible involves that in part. You use the math to help you check credibility. So I rule out these by using the math model. I rule this as being not credible, but not because of the math model, sort of as a separate issue, right? And it has to do with the psychology that this is a kind of one that you might designate as one that you'd think of, but might not occur any more likely than this. If you actually were thinking about this one, your point, if you were thinking about this one as the target and somebody said they got it, you would be equally unimpressed, you'd think it would be incredible. Okay, well, let's leave that. Well, so the point, okay, so I think those things are really important. What I want to emphasize now is that one of the big parts of this, of course, the simplicity of the model is it's binomial and then it's normal approximation, and the normal is characterized by just the two parameters, the mean and the variance. And so and then the standard deviation is this same shape, so there's a standard thing. So you think about it in terms of how many standard deviations you are away from the mean. And that's sort of the thought process. Now, the power of this central limit theorem is that it does not depend on the binomial distribution. It's true very generally. So therefore, it's something really worth knowing, and we're going to talk about that a little bit. So, an application that would be good and is a nice one. So this is sort of the first of a couple of projects that I think of as entertaining, is to think of stock prices. So actually, this is a place where many of you may be doing this already. You might be tracking. You can easily track the stock prices of various stock prices online. And whether you have any money or not, even if you have no money, you can make your own portfolio and follow how it's doing, and you'd be doing all this stuff, which is interesting and so forth. So you could be doing that now. And so the thought is you might think about the succession of stock prices and how they evolve, and you make a model of that. Now, the point of this is there's a certain element here where it's going to be in the domain of the central limit theorem. And but it's not exactly clear. So the point that's interesting is the contrast is the coin tossing is so close to the math you don't even realize you're making a mathematical model, right? It's really, we believe it's close to a half, it's independent, things are pretty clean. When you go to the stock market prices, everybody's wondering what to think of them, right? So first of all, some people know stuff, some people don't know stuff, but you can just take the point of view that if you don't have any, if you don't have any information, if you're doing academic stuff and you're not paying attention to reading the newspaper too carefully, or you don't know any more than anybody else, you could say, how do I think what's happening in the stock market because somebody else's inside information isn't privy to you, so from your point of view, you don't know which stocks are going to go up or down because you don't know the circumstances. So taking a point of view of sort of ignorance, you are looking at the stock market prices. Now, I'm thinking that the stock market, so here's stock market price. Stock market price on day n. So what I want to consider is mathematical models of this stock market price and what we might think would be, how, well, what I'm headed for is I'm headed toward the normal distribution that somehow the stock market price, if you think about looking at today, you're going to look, say, 2 months from now, and you're going to think you're going to have, every day you're going to have changes. So there's some stock market, you start, this is at time 0. So we know the stock market price today. You pick any stock, you know it today, and you want to know what the stock market price will be after n days, where n is something big. Maybe 60 days or at the end of a year or something like that, right? So you have the stock market price at the start, you know this. And you wonder what you're going to be there. And so I propose that, this is not a novel idea, but the idea is that you think of a mathematical model of this, and then you think about what that model implies. And the thought is you might actually, there's more than one model, so there's a bunch of models. And there are all sorts of things you could think about, but this is pretty basic to what's going on. We're not doing anything fancy. We're not talking about options and puts and all this stuff. You could mess around with the stock market price. We're just thinking about what is the price as we go through time. And then I'm thinking, well, okay, so one model, model 1, is Sn. This is the initial, the stock market price at day n is the initial price plus the change, some increment between S0 and what it'll be at time S1, plus X2 plus. In other words, there's a change at the first day, and a change on the second day, and a change. And you think of these changes as IID, independent, and identically distributed, as approximately. Now, things are not, units are not divisible necessarily. There might be some restrictions to what we could have. But then this is a model of what's happening. And this is sort of an approximation. And then these x's, the x's have some distribution. So probability x less than t is f of t, some distribution. And there's a mean and there's a variance. Now the point that's the reality part that's interesting, that makes this, there's several things. One part is, well, this is the stock market prices. This actually is something people would think of doing. The one point is that this distribution of the change, if this is, it might be reasonable that the change over successive days are approximately independent. Okay? And they might have the same distribution. So you might have this, but this distribution is certainly not going to be plus or minus 1. It's not going to be binomial. This is not going to be a plus or minus 1 thing like heads and coins. It's going to be some general distribution. And it's going to have some mean and variance, say. So there is a model, and this is the first random walk model. And a random walk is when you take a sum of random steps. So these, you can think of these as steps, and you take the first step, second step, and then this is the position. You start off here, and this is your position after taking n steps. So those x's are the random steps that you're taking. And then you're looking at where you are after n steps. And as you think of that as a function of n, that's a stochastic process. And if they were independent and identically distributed random variables, this would be a random walk, but they could have a general distribution. I'm not saying anything that this distribution is not normal, it's not binomial, it could be anything, but it's got some mean and variance. And that's sort of realistic, because you know the distribution. This might be roughly correct model, but the distribution's not going to be anything. One day is going to be, well, and you can investigate this, right? You could go collect the data. You could see the changes. You could look at the stock prices at the end of the day, every day for a year, and actually look at the increments and estimate the distribution. Okay? And you can do this for lots of different stocks, lots of time. That's easy to do. So you can actually estimate what this F is and estimate this. You could fit this model to the data, which is an interesting experiment. So this is the first random walk model. Now, the perfect point of this is where this fits the theory is the theory says that when n is not too small, like maybe 10, after a week or two, to say nothing of a month, the distribution of this Sn, given this model, will be normal under these assumptions, regardless of this F. Whatever F is doesn't matter. Of course, if F is strange, maybe n has to be bigger. But as long as F is not too strange, even after about 10 steps, the random walk, this final position is approximately normal. So the central limit theorem is saying here, let me just put that here, the central limit theorem is saying that Sn is approximately normal with, well, I can put it this is S0 plus normal with mean n mu, variance n sigma squared. In other words, you just add up the means and add up the variances, right? Because for getting S0, the mean is the sum of the means, the variance is the sum of the variances, assuming independence. So this is the same thing, equal in distribution as normal S0 plus n mu n sigma squared. Independent of the F. So no matter what kind of distribution those steps are, it's going to be approximately normal. So, I mean, this is a point of view. There's a model. So it becomes interesting whether this model is realistic. You can certainly take data and estimate F for any stock. Just take the day, 365 days in a year, estimate this, see what it looks like. Estimate the mean and variance, just by computing averages, right? So you could estimate, you could fit this model to data easily. That isn't proving the model's correct. I'm just saying you could actually collect data on the changes in the stock market price and fit F in this to, assuming the model, you could fit F in mean and variance. And you could do that for one stock over 1 year, 1 month, 2 years, whatever. You could do it for lots of different stocks, and you could see how the F's are different, means are different. This is certainly not, you know, this is what people are doing in some variant, right? Because the one you're going to want to invest in is going to have probably a high mean. You're going to want to do this analysis and say, oh, this one's got a bigger mean than the other one, you know, hopefully positive. The last week doesn't look so positive, but anyway, hopefully you're going to want to pick the one with the big mean and invest in that one. And you may also want to pick the one with the big mean and the small variance, because you don't want to have risk. Okay, well, so one extra project is to investigate random walk models in some way. That means you could look at data, you could look at literature on random walk models. So this topic. Now, I have the point, this is a topic. Random walk models of stock market prices. This is a classic problem. People have been looking at this for ages. There's all sorts of books of various sorts on this, like there's a great book called A Random Walk Down Wall Street, which is talking about, there's all sorts of nice stuff about this, which is about stochastic processes and about part of the course. And it's sort of like you could be focusing, so you could make a special project for yourself where you focus on finance, which would be great if you're really interested in that. Okay, now the part I want to go on to, though, and makes part of the project interesting, is you'll notice this adjective here, which I haven't explained. I said first random walk model. So there are actually two other models that come into play fairly naturally. And there are more, but there are other models. But actually, the central limit theorem or some variant of it still comes to play. So the math is still there to help you. The model's a little different. So the idea is you again you're thinking of this, but now you know this, you start here. And you're thinking of this, how do you get from here to here? And the point of view here is that this story doesn't make so much sense in some cases, because let's suppose that you start off here at 100. The share price at this instant of time is 100. And you take a bunch of steps, and somewhere later, it's gone down to 25. Things are not so good, right? It's gone down to 25. So you started at 100. At this point later on, maybe 2 months later, things have been tough, and it's down to 25. You're now here at Columbia. You're now shifted in response, you're eating only oatmeal. Okay, your situation's tough. But it's at 25, and the reason you don't believe this model anymore is because the price is much lower, so you expect the increments to be smaller. You expect them to be relative to the current price. In other words, some sense, the higher the price, the higher the increment, because it's sort of per dollar. So there's a different model. The model is that you start with S0 and you multiply, well, not by increments, but you multiply this to say that there's multipliers. So whatever the price is, there's a random multiplier that's independent. So now it's random. It's a multiplicative model. And you believe that the current price is multiplied by an independent and identically distributed random variables. Every period it's multiplied by something rather than added. So now if the price changes up and down, the increment's going to be affected correspondingly. Now, just to give you peace of mind, I'm not making this up myself. This is a serious issue. So you have this multiplicative model. So the question is, how do we proceed if this is our model? Well, now we think this is also, these xi are again IID, and there's some f, but they're multipliers. They're not added increments, they're multipliers. So how would we proceed here? We want to do something like we did before. What would be the obvious? We now want to analyze how this thing behaves. It's now multiplied, and how would we? So somebody say something. It's probably in your mind. It's got to be in the mind of somebody here. You're going to do something. You've changed the model. You're going to let the successive prices be the initial one with random multipliers, where the multipliers are random, independent, and identically distributed. And you want to know how to know what the distribution of this is, approximately. Yeah?
You should take the log. So
Yeah, there's the word. One word. One word here. One word that you... Yeah, I didn't let you say all the things you wanted to say, but this is all that I'm thinking of. All I'm thinking of is you should, there's a takeaway from all that calculus. Exponential, logarithm. Okay, this takeaway is what this does for you. So you should take logarithms. Okay, but that should be obvious. You see multiplicative, you want it additive, you take logarithms. We're going to be, in a lot of the stuff that's going on in stochastic processes, you use exponentials and logs, very important ways to convert sums and products into the right things. So here we got a product, and we don't want a product, we want a sum. So if we take logs, we're in business. So this is the second model, the second random walk model. And if we do this, notice that we will have log of Sn equals log of S0 plus the sum of the log of xi, I equals 1 to n. So if we call this Sn prime, well, let's see, let's call it Mn. The point I want to emphasize is you believe somehow that the model is more appropriate to be multiplicative. But having done that, as soon as you take logs, you're back to the same model you had before. Right? It's the sum. The log of the price is the initial log plus the sum of all the logs, which if the x's are IID, log of xi will be IID. In other words, you start off by assuming all of these are independent and identically distributed, then all of these also will be IID, with a different distribution, of course. I mean, this has some distribution. This has got, let's think of that. That's this log. So the probability that log of x less than or equal to t equals, now, all we do is just take the exponential of both sides. So this is probability x less than e to the t. So this is, for whatever the distribution of x was, the distribution of y is the distribution of x at e of t, right? So something. So there it is. But then this says, what does this say to us? This says that Sn, well, let's start with log Sn is equal to log S0 plus normal n mu prime n sigma squared, well, let's say bar, put here, where these are the mean of the y, let's say, the expected value of log x1 is mu bar, and sigma squared is the variance of log x1, right? So we have, again, mean and variance, but they're the mean and variance of the logarithm of the xi. So this is the same thing as before. After I take logs, I have another random walk. Now this seems a little bit crazy and complex, but what I've just done, this second model is commonly accepted, whereas the first one, this change from first model to second model is what people believe, mostly. I mean, except they may not believe it at all, but if they believe it, they believe this more than the other one. So this is the second random walk model, where it was initially multiplicative, and now after taking logs, it's again additive, again a random walk, and we have this alternate model. So then what do we, if we do this, what does it tell us? It tells us, what does it tell us about Sn? It says Sn itself is equal to e. So I just take the exponential, e to the log of S0 plus normal n mu bar n sigma squared bar, right? This is, I take the exponent, the exponential of the left side is just Sn, and I take the exponential of all this stuff, which is this. And then the exponential of the sum is the product. So this is e to the log S0 times e to the normal n mu bar n sigma squared bar. And this is just S0. So we have a new story. The second model produces a new story. It says the random walk price after n days is now, by this new model, is the initial price multiplied by this. But it's multiplied by the exponential, e to the normal power, a random normal. The normal still appears, but it appears in the exponent. This distribution here, the exponential of a normal, is a log normal distribution. this quantity here. So, I mean, one of the things you could do with data, so this is just to illustrate the data, you now have two models. You have the simple additive random walk model, and you have the multiplicative model that tells you that the price is going to be log normal. So one way to check the model is to see if the price is actually, if you look at start at some point and see where you end up, is the price actually look like it's normal or log normal? Or something else. I mean, maybe the whole model doesn't fit. So then this is, now actually the point is you automatically get an issue with the data to say, well, we've got a normal model that says the distribution should be normal, but once you make it multiplicative, it says it should be log normal. That question might be, it might be neither. You know, what does that mean, right? Well, the models presumably, neither of those models are correct. The point here is the central limit theorem operates with great force. So if the model is correct, the first model is correct, the distribution will be normal or close to it. If the second model is correct, the distribution will be log normal. Those are reference points for the real world, and with the real world, to the extent that it looks like that, maybe the model fits. To the extent it doesn't, the model doesn't fit. Part of this stuff here depends, the key assumption here, what assumptions are there? Well, one assumption is these random variables that we add up should be independent and identically distributed, or approximately so. It doesn't have to be exact, but approximately so. And they don't really have to be identically distributed. It doesn't matter too much as long as no single random variable is huge compared to the others. But one point that's important is that you have this finite mean and variance. That puts a lot of constraint. You don't have humongous values. So one problem that could occur is if you have some huge possible outcome, that could be out of scale. Maybe the variance isn't finite. And that's key in this theorem, that you have finite mean and variance, and that mean and variance comes into the normal. If you don't have a finite mean or variance, or one of those, you have yet a different model. So that's kind of a third random walk model, is variance of the first two where the variance is not finite. Okay, so that's three random walk models. So you could look at that, and the perspective would be, there's two perspectives. One is there's a literature on this. So a lot of people have written books and papers on random walk models, and sort of pros and cons and so forth about all of that. And that sort of gives you a perspective to think about stock prices in terms of these models. It's a major issue underlying finance. Okay, so you could think about this model from the literature, or you could actually do it from a data analysis point of view. You could actually just look at all the data and start seeing if this stuff, how well does this stuff fit for yourself, which is kind of a nice way to proceed. One of the nice things to do is, when you're doing probability and stochastic processes, is to directly experience the stuff. In other words, if you can simulate it all. You can just sit there easily on your computer, simulate stuff that's going on, the random stuff, and see what happens. So if the probability distribution is supposed to be normal, just simulate the random walk and see if it is normal. And if the theorem, if we're telling you that it's normal, you sure as heck ought to see when you do your simulations that it's always normal. In other words, all this stuff is like that in the course. It's not like it's unreal. You should be able to just do computer experiments very easily and see that everything is exactly like it says. If it's not, there's no point in it, right? I mean, so it's subject to verification in a way that's easy to do. So anyway, I invite you to take that attitude to actually check things out. So one approach to this special extra credit project is to do something about random walk models. And on that topic, related is a second project. And the second project is this book. This is Peter Bernstein, Against the Gods. the remarkable story this. And the idea is you'd read that book and write something about it. That's it. Now, the only constraint is that you not have already done this book for another course, right? That you do it as if you've done this for another course, that's not fair. But if you were to do this thing and read the book and then write about it, and this book is about Against the Gods, remarkable story about risk, is about probability and the real meaning of probability. So it's a great book in terms of, it's not going into math models, it's going into what's the history, what's the implication, how important this is to dealing with uncertainty. So the question of how we deal with uncertainty, which is the sort of practical issues underlying what the course is about. So it's a nice, very nice book, nice to read. So this is yet a second project. Okay. Now, let's continue. I haven't gotten here yet. That's a third project here, but I want to get to here, so let me say a little bit about that. I may lapse on into that. Okay. Okay, this is this. Now, I want to talk about transforms. So I guess this is where in the book. This is a place in the book. Yes. This is, well, this is, yeah, transform is section 2.6. So it's ground that you're covering now. I guess it's on the second homework. And it relates to this problem very nicely because the transforms actually play a very nice role in understanding and proving the central limit theorem. So there's a tight link between this transforms and the central limit theorem. But, and this is so this is an interesting topic which you might know a lot about. Like if you have background in electrical engineering and you're doing something related to that, you might have learned a lot about transforms. So transforms are used a lot in electrical engineering, signal processing, and so forth. You could conceivably have been doing a lot with transforms, or you might never have done anything with them at all. That part, we want to remove that situation so that you know about something about transforms. And in the book, the transform that's discussed is the moment generating function, and that's defined this way. But what I want to do mostly is communicate what this is all about. Why are we talking about transforms? And maybe I should go further to write what this is here. This is, say, in the continuous case, or it's right. This is continuous and discrete. So here is the moment generating function. And this brings a couple of things to mind. It brings to mind that you might think about how to compute this. This is computing the expectation of a function of a random variable. And this is one such. This is a function of a random variable. I mean, I have the random variable x, and I'm looking at e to the tx. And of course, as I was just saying, the log and the exponential, here is the exponential. Here's, again, the log exponential stuff is being exploited in this transform. So the transform, just like that multiplicative example, this transform is introduced deliberately to produce an exponential function in the picture, to exploit log exponential prop. This right here is the point, part of the point of this. But then the point here I want to emphasize is you want to be clear about what this means. And there are actually two ways to express this, and they're equivalent. So one way is to think of well, if I write it in terms of this, I would write this. This is sort of a straightforward for the continuous case. Well, or I could have in other words, I could treat this as an object, h of x, and I could have the distribution of h of x here and just take its expected value. Or I could have x here and have its distribution and have integrate this way, right? This would be to say h of x itself is a random variable, and I could talk about its distribution and compute the expected value in the normal way. Or I could have x as a random variable and then compute this. Right? That's sort of two ways of writing this, and you could think of this way, and I've written it. And then this is, of course, that's the continuous version, but there's a continuous version and a discrete version of what this means. Now, the point I really want to emphasize is why we're doing this and how you think about this in a high level. I mean, what you're doing here. So I guess I would, if I this thing doesn't move in any good way, but let's suppose we have x, but it's got a density. So suppose we're in this case where so the probability that x is less than or equal to t equals minus infinity to t fx x dx. So x is a random variable. Its distribution is here, and it's got a density. So we're in a continuous case, just for discussion. And so when we talk now, point of view, when we talk about x, we're really interested, because we're doing probability, in its distribution. And its probability distribution is captured by its density. It happens we're assuming it has a density, so this is a characterization of its distribution, or this would be its cumulative distribution function, both characterizing the distribution. So this function is characterizing the distribution of x. Now, this transform here is really what we're doing is we're making a mapping between fxx and phi of t. I could put this here. I could also write, to emphasize, I would put this x subscript to emphasize that this transform is referred to, applies to x. But we have this function. The point here is this is actually a function of t. Well, it's also a function of this x, but for x given, it's a function of t, not just one t, but a function of t. So when I go here, let me just emphasize this. This is a function of x. This is a function of t. The important idea is that the probability density is a function of this variable x. You know, it's a picture like if it was normal again, it's some sort of thing. This is the fx of little x, and here's the possible little x's, and this is some density, right? That's the some density. That's this thing. This density is a function of little x. And this transform is a new function. It's a function of t defined in this way. So it takes this function, here's this function in here, and we integrate with regard to this variable, and we do this, and in the end, this variable, this function of x, by this process is converted into a function of t. One function's mapped into another function. The distribution of x is characterized directly by this density, this function. The point is you want to think about functions. This function is mapped into this other function. And the function you started with had this variable x, and this is this variable t, which appears in this funny way. In some way, you've put this t in the exponent, and now you made a new function. So you've transformed one function into another function. You do so because somehow that's going to help you, right? It's a trick. You start with one function, you want another function, you transform the other. There's lots of ways you could transform one function into another, and there are lots of different transforms for doing that. And the point is, you want to have a lot of, it's going to do good things for you. That's what we want to discuss. It's going to do good things for you. But at a high level, you want that this makes sense. In other words, what are you going to do? You're going to start with x, which has this. So you have this density. You're going to construct this function of t now that's the transform. And you're going to do something with this function of t and then have some new distribution, right? A new transform. So you're going to want to do, in this picture here, you're going to do something like you're going to have x, and then you're going to have this function, and you're going to do the transform, and you're going to get this function, and you're going to do something with this transform maybe, and you're going to get a new transform. This is some operation that goes from x to y, but in transform space, and then you're going to go back to x has a density here, y has a density here. You go to transform, you transform to transform space, you do something in transform space, you get another transform here, and you come back here. You want this story to make sense and be descriptive. So in the following thing you want to have happen is you want there to be a one-to-one correspondence between these densities and these transforms. So that when you go this way, you can come back. You go this way, do this, and when you come back, you've uniquely characterized the distribution of y by this. You work here. This is transform land. You sort of sit in one world, and you go to the other world. So you start in distribution world, and you want to go here. You want to understand how to go from x to y. How is it distribution related to this one? And this is hard. So instead of doing that, you transform, do it in transform space, and come back. That's why the word, it's called a transform. You transform here, but there would be a unique correspondence. So when you do this and come back, you know that you've totally pinned this down. Okay, this is just sort of the high level of what's going on. So, moreover, in the central limit theorem, the central limit theorem as its statement, one version of the central limit theorem, would say if these x's are IID with the expected value equal to mu and the variance equal to sigma squared, then you're going to have x1 plus xn minus n mu divided by n sigma squared square root. So this is the mean of the sum, and this is the variance of the sum. This is going to converge to normal 0, 1, where we mean in distribution. So this is going to say that this random variable, its probability law converges to standard normal. The way we could prove that is to take the transform Okay, so the statement is, you take a sum of random variables, they're independent and identically distributed, you subtract the mean to make it have mean 0, you divide by the square root of variance to make it have variance 1. So this random variable for each n has mean 0 and variance 1, but moreover, for whatever distribution it has, if you let n get big, the distribution will go to normal. It'll have to have mean 0 and variance 1 by this scaling. But you force that central limit theorem saying is that whatever this distribution was to begin with, the distribution of this scaled thing is going to be normal, under the assumption that it's got finite mean and variance. And the transform is, if you take the transform of this thing, the transform of that's going to converge to the transform of the normal, and that's going to be a proof of this because not only is there a unique correspondence, but there's a continuity result that says if you have a bunch of transforms, so if if you consider, say, Zn, well, you consider, phi of Zn of t, and this goes to phi of Z of t. So here's some random variables go to a transform another thing, then it's going to turn out that the Zn's, these things with minor regularity conditions, are equivalent. Convergence in distribution of random variables is going to be equivalent to convergence of the transforms. Not only is there one-to-one correspondence, but there's a correspondence in limits. So you can work with, if you want to know what's happening to this, you can work with the transforms. And then when you do this, it's going to be actually surprisingly easy. Okay, well, we're going to continue this. I could rant. I'm in risk of ranting on this topic of transforms a little more.